I'm studying or whatever recently. Is there anything that you wanted to ask about related to chapter 13 before we start some new stuff? We can take a little bit of time and do that here. Grace?
Can you do like how to find the maximum and minimum of the LI?
The calculator piece?
Yeah.
Yeah, we can do that. Did you have a particular problem that you wanted to look at?
No, any of them.
Okay. So I'll just take say number 2 from the problem set. That was a find the zeros for this, and we can do the limit notation on top of it if you'd like. Put a date on this. 5/22.
Can you find the zeros for this as well using the calculator?
Yeah, we can do that, sure.
Gracias.
No problem. All right, so I just go to the y equals menu, and I'm going to type in whatever I got here. Oops. So x cubed plus x squared minus 6x. And I can hit, if I haven't graphed anything in a while, maybe you do zoom standard so it resets your window back to the standard. And oopsie-daisy, I have my axes off because I turned them off for a different class. So turn that back on. It's unlikely that would be your situation. I don't think there's any reason why any of us would have turned the axes off. Anyways, so here's my graph. So I see I have a local maximum here, and I know it's local rather than global because there's still some stuff that's higher up than that part is. And then I have a local minimum down here, and I know it's local as opposed to global because I got some stuff that's lower than it. And that's it for the extrema. Now it's a question of just finding those points. To find those points, we're going to use the maximum and minimum commands respectively. To get to those, we press second and then the trace button. And then we'll use the minimum command to find the minimum, the maximum command to find the maximum, and Joe, if you're looking for the x-intercepts, we'll use the 0 command from this menu to find the x-intercepts. So let's just kind of knock these out one at a time. We'll do the maximum first. So at the bottom now, the calculator is going to ask me 3 questions. It's asking me for a left bound, right bound, and guess. So the left bound is first, so I just need to move my cursor using the left and right arrows so that it's somewhere, anywhere on the left side of that maximum. But we really want only one maximum kind of in between our left and right bound. So it doesn't really matter.
Okay.
But like if there was 2 of them, you wouldn't want to pick your range so that there's like 2 maximums in between it. Right? If you have a left bound and a right bound, you don't want 2 humps in between it because the calculator will just find, you just want one of them in between. Right? So like I'm going to pick here, press enter. Now for the right bound, I'm just going to move over here and press enter and then hit a guess. So there's my maximum. I just write down the point negative 1.7863 comma 8.2088207. So that's just the point. Grace, what I'm saying there with the range, it doesn't super matter, but like say I was looking for a maximum, I pick 1 point here, and then I pick the right bound to be like way over here.
Okay.
Now there's like 2 maximums in that range because there's the local one over there, but then the points on the right side are higher than it, so it's like the calculator could get confused.
Okay.
But as long as you're like kind of sensible and just pick like, so there's only like 1 high point in between them, it's fine.
Yeah.
Yeah, I know that seems kind of confusing or whatever. Okay, do the minimum next. So it's the exact same command. So we just go second trace, pick the minimum, It's going to ask me the same 3 questions. I kind of do things the same way. So start by moving my cursor so that it's on the left side of the minimum. Anywhere on the left is pretty much okay. And then, oh boysy. Go to the right side of my minimum. That looks fine. Guess, just press enter. And there's my minimum, so like 1.119634, comma, negative 4.060673. And then if we wanted to do the extrema, or the end behavior using that limit notation, there's my pen. So to do that, I'm going to have automatically these parts I can write whenever I know that what I'm taking the end or describing the end behavior for is a polynomial, which clearly it is, right? In fact, everything we're using in this chapter has been polynomials. So I know this much right away. So the piece down here is just telling me whether I'm talking about the left end of the graph or the right end. So negative infinity is talking about the left, the positive infinity is talking about the right.
So is there always 2?
For a polynomial?
Yeah.
Yes.
Okay.
Yeah, because you know there's arrows at either end, right? So if I look at the left end, what is that arrow doing? Pointing down, so down is negative infinity. And if I look at the arrow at the right end, it's pointing up, so it's positive infinity. Yep. So that's the way we use the limit notation. Leo, she's just telling you that the test is moved to next week.
Nice.
I can see you're devastated.
No, Owen told me this morning, actually. I was so sad.
Okay. That you just had time to get over it then.
Yeah.
Okay, that makes sense. Grace, does that feel okay?
Yeah, that's right.
So Joe, to get the x-intercepts then, or the zeros, the real zeros is all you're going to be able to find. You can't find the imaginary ones with the calculator.
Okay.
But if it says just like, the real zeros using your calculator, or the x-intercepts, we press second and trace. We're going to use the 0 command, and we're going to do the same thing. We'd have to do it 3 times. I'm just going to do it once because it's like the same thing 3 times in a row. But it works the same way. It's going to ask for a left bound, right bound, and guess. So let's say we're looking for this one here that looks like it's at -2. So anywhere to the left of it, so where the cursor's at, is fine. And then anywhere to the right of it, that looks good. I'll press enter again. And then for a guess, where you're at is fine. So my 0 there would be 2. So sometimes we list them like as just the x coordinates, like the zeros here look like -3, 0, and 2. Or you could write it as like 2, that ordered pair 2, 0, comma, 0, 0, comma, -3, 0. You could write it that way also. That's fine.
Sounds good.
Okay with that one? Peyton, you had a hand?
Yeah. I don't really get like multiplicities.
Okay.
It's on the page.
Yeah.
Like I get how to do like the zeros and the extrema,
Mhm.
but I don't get the multiplicities.
Okay. So a multiplicity is just when you get one of our zeros occurring more than once. So like, let me just make one up here real quick. My good calculator that could do this quickly is out of batteries. So I'm just going to have to make one up here for you real quick. So let's just say that we have x to the 4th plus 4x cubed plus 20x squared plus 64x plus 64. Okay, so I just made up this problem as an example. So I know that this should have 4 zeros exactly, right? And my possible rational zeros are just going to be the factors of 64 divided by the factors of 1. So the factors of 64 plus or minus 1, 2, 4, 8, 16, 32, and 64. Okay with that?
Yeah.
And then we'll go and look at our graph. So let's see what our graph can tell us. So I'll go and type this guy in. And we'll just hit graph and take a look at what's going on. All right, so I see an x-intercept here at -2, but that's all I see. Right? Now, two things could be going on. This might be used a bunch of times, or, well, I can't see past -10 to +10, so these guys just might be happening but off the screen. So let's check to just real quick to see if they're happening off the screen. So I'll just reset my x min and max to be -64 to +64. I doubt they're off the screen. I know what's happening because I made the problem up. But, you know, let's just be careful, right? I do that, and I don't see anything happening out here where anything's crossing. So I feel pretty good about this being the only thing. I'm just going to reset that window back to what it was before, where it could see things nicely. If you notice, though, there is something special about the way this graph is crossing or intersecting the x-axis. You see how it's just kind of touching it once and not actually passing through it? So this was a special situation. This is called a bounce. We talked about this in a theorem. Oh, Boise, it was way back there. It was one of the first couple lectures in here. Maybe it was the second lecture then. Let's go back and find it real quick. There it is. So we had this bend, bounce, straight theorem, which can be really helpful in identifying if a multiplicity is possible. So if a graph passes straight through, that 0 can be used only one time. If it bounces, like we're seeing in our graph, it could be used an even number of times, so like 2 times, 4 times, 6 times, etc. Or if you have a bend where you have like half of a bounce going like down and half of a bounce going up, it's going to be used an odd time, so like 3 times or 5 times or 7 times. So we know that, oops, that's not what I wanted to press. So if I look at this guy, we know that this is being used either 2 times or 4 times, since we have at least 4 zeros. Everybody, you're okay with that?
Yeah.
So if it's used 2 times exactly, that means the other 2 zeros would have to be imaginary because we can't see anything else. Or it could be used 4 times and there could be no imaginary zeros. We don't know which one's going to happen yet, but we can find out here really quick by doing the synthetic divisions. So that's where I'm going to go to next. So far, so good? And you see the fact that if there's a multiplicity, like we know there's a multiplicity going on in this problem, it doesn't really affect what we're doing too much. It just, you know, have to remember to make sure that when we do our synthetic division here, I'm going to use -2 at least twice, right? And it's critically important when we do that second division, we're using the result of the first division, right? So far, so good. So if I start to list my zeros, I know I have -2 that's using twice. So we'd say that's a multiplicity of 2 because it's being used twice. And then this piece just is a quadratic that I can set equal to 0. And I can solve. You could try doing another synthetic division on that. It's not going to work because I made the problem and I know it's not going to work. But even once you get down to a quadratic, I would always kind of stop there and do the quadratic formula or try factoring it or solve directly or some other method to solve the quadratic just because you know you're going to get answers out of that, and the synthetic division is kind of a guess. Like here, we don't know it's going to be used, whether it'll be used twice or 4 times. So I'm just going to use it twice and then solve the quadratic. And if I end up using it 2 more times, the quadratic formula will catch that. And if it's not, the quadratic will tell me the answer to that. So like I can't do anything wrong there. You know what I mean? Or waste time doing something that doesn't work. Does that feel okay?
Yeah.
So you could solve this with the quadratic formula and that would be fine. I'm going to solve it directly though, since there's no x term. There's just x squared. So I can just like subtract 16 from both sides, square root both sides. Square rooting both sides gets you the plus or minus. Because it's a negative under the square root, we're going to get the I, and then the square root of 16 is just 4. So that would be plus or minus 4i. So what we saw is that we did get a multiplicity of 2 for the -2, and we got 2 imaginary solutions. So it was the one where it was used twice and not 4 times.
Okay.
So the multiplicities doesn't really change much in what you're doing. It just like the possibility that maybe you can do one of the synthetic divisions, use that number twice or 2 times or 3 times or 4 times or whatever. Does that feel good?
Yeah.
That's what you needed?
Yeah.
Is that everything's pretty clear? Okay. Yeah, no problem. It's just kind of a weird vocab thing, right? That it doesn't really change much of what you're doing. And again, the graph, looking at the picture, gives you a good indication of whether a multiplicity is possible even. So it's a nice clue to like, oh, hey, look at that. Better plan on using that one twice or 3 times or whatever. Grace? On the review, question 2C, this one here?
Yeah.
Sure. Yep. All right, what does it say here? Determine whether the real zeros for the polynomial lie on the interval from -2 to 3. You must support your answer algebraically, okay? So here, what I'm going to use is this theorem that we talked about probably on this day.
I like get how to do it. I just don't understand like the upper and the lower bound.
Oh, okay. I'm just going to find this theorem and point it out to show everybody. So we did this on 314. So this is the theorem we're using. This one I've circled in yellow. So basically it says if k is positive, and when you do the synthetic division with k, all the numbers that you get as a result are greater than or equal to 0, then that number k is an upper bound for all your real zeros. So in our case, if we look at this, the number we'd be picking for k is going to be the 3, right? That should be the upper bound. And the lower bound then would be the -2.
So the x follows
Well, this is not a coordinate, that's an interval, right? It says interval. So that's like all the numbers between.
So the negative one will be the lower bound, or like the smaller one will be the lower bound and the higher.
Yes. And in fact, to use that theorem that I was just pointing out to you, the lower bound has to be a negative one and the upper bound has to be a positive one in order for us to use it, because we need the k to be non-negative and we need the k to be an upper bound and we need the k to be non-positive to be a lower bound. So you actually have to have like, you can't have like two positive numbers or two negative numbers and use this theorem. Which again, like I wouldn't give you a situation where you couldn't use the use the theorem. So that's just telling me what I'm going to be using my synthetic division with, right? So I'm just going to do my synthetic division. So when I set this up, we have to be a little bit careful because notice I don't have any x squareds. So I have to make sure I put that 0 in there. But I'm just going to do two synthetic divisions, one with -2 and one with +3. Again, because those were the bounds of the interval that I was given. So we do this. So I have here non-negative, non-positive, non-negative, non-positive, non-negative, since those are alternating. That means -2 is a lower bound. So I'll say yes. And we'll do the same thing now with the next one. So here, greater than or equal to 0. So this is basically, that all works, right? This one, though, already fails because these have to be all non-negative. So like all of these are bad. So this one would be no. 3 shouldn't be an upper bound. And you can check this pretty easily to see if you've interpreted this correctly. So I'm just going to go ahead and take a look at the graph, because this theorem is just about the real zeros. It's just going to be x-intercepts anyways. So if I can take a look at the picture, I can tell right away whether something should work or not. So -2 is over here. Right? And it's all the zeros are bigger than that. But 3 is here, and I see that one of the zeros is actually bigger than 3. So I know 3 shouldn't work. Is that?
Like one of them is no, then like the whole thing is no.
Right. Yeah. So if one of the numbers at the bottom doesn't fit the pattern that you're looking for, so for the upper bound, they all have to be non-negative. And on the lower bound, they all have to be alternating. Then one number not working is enough to say the whole thing is broken and it doesn't work. And again, if you're not sure, you can look at the picture and for sure at least tell the lower bound and upper bound part, like answer the yes or no. Even if you can't algebraically support your answer, you just, you look at the picture and it's like, is everything in between -2 and 3? No. Where are we outside? Well, the 3 is the one that's, too small. If we had repeated the same thing with 4, though, it would have worked. Does that make sense, Grace?
Yeah, that's good.
Okay. Joe?
So for this problem, when you're looking at 1, -6, 12, -16, 22, like those numbers, those are in relation to -2, right?
So this is about whether -2 is a lower bound.
Yeah.
So all I'm doing is checking to see, is this non-negative? Is this the next one non-positive? and then I want non-negative. I just want them to alternate between them.
Okay.
That's all I'm looking for.
Okay.
So if it started with a negative and then positive.
That's okay still. Yep, that's okay still. That's still alternating. Doesn't have to start with a positive and then go to a negative. It could start with negative and then go positive. That's okay.
But if like one of them messes it up.
But if you have two in a row that are the same,
Okay.
done. Doesn't matter where that two in a row happens. So if it happens at all, it's done. And you should be able to tell by looking at the picture before you even do the synthetic division whether it's going to work or not.
Okay.
Right?
Okay, thank you. That's good.
Okay. And that probably helps, knowing that like I can just look at the picture and kind of know what's going to happen in advance is kind of helpful, right? Not that this is hard, but like if you get second guessing yourself about like, oh, what was the pattern I'm looking for down there? You can at least do the synthetic division and be like, okay, this one doesn't work. I can't tell you why it doesn't work, but I know that it doesn't because I looked at the picture and I know it doesn't. You know what I mean? Like,
Thank you.
yeah, you're welcome. And again, this was something that's like was very useful pre-graphing calculator being commonplace, because it would like really kind of, it tells you a lot in terms of like, okay, if we're going to go look for one of these things, how would we go about finding it? But like with the graphing calculator, it takes 2 seconds to get the same information just from looking at the graphing calculator, and there's no like guess and check involved, which was kind of what we were doing back in the day. It was a big hassle doing this when I was a student. But like you really got good at synthetic division because you had to do a ton of them. So it was like, in some ways it was, you really had to understand what was going on. Anyways, last call on chapter 13 stuff. Okay. Again, if you change your mind or whatever, you can always come back and talk to me during community time or whatever. If you need to do that before the test, not a big deal. But I felt like we had a lot of good questions there, probably clarified a lot of stuff for people. So, do you guys feel pretty good? Okay. We're going to chapter 15 next.
Oh, we're skipping 14.
We are skipping 14. So we're going to talk about here exponential and logistic functions. So in this chapter, we're going to look again at exponential functions, logistic functions, which would be new to us. We looked at exponential functions last year in Algebra 2, and also logarithmic functions, which again, we looked at last year in Algebra 2, but often is one of the haziest topics for students. When they look back at Algebra 2, they're like, yeah, I didn't understand what we did with that at all. So it's a good thing to review. Just as a heads up, this is going to be some new stuff, but then some stuff that typically doesn't retain real well also. So this can be kind of maybe a tough chapter, just kind of depends. It's also pretty long, so we'll be here for a minute.
This is the last chapter we're here.
Probably for the seniors, maybe. For everybody else, we'll do at least one more after this one. The next one's I think is a pretty big beefer too. So that might be these might be the last two. We'll just kind of, we'll play by ear kind of thing. All right. So we're going to start by talking about exponential functions. So we're just going to define that. So our exponential function is something of the form a times b to the x. We call a the initial value. You could also refer to it as a coefficient. We call b the base. Maybe we'll say base of the exponential. And I guess, Mr. Kulik, you really need to be a little bit careful here because that value for b has to be positive and not equal to 1. Should make sure I get those on there also. Let's think for a moment here why Mr. Kulik is requiring the base to be positive and not equal to 1. Let's start with the 1 part. What would happen if b is 1? We would have a times 1 to the x, right? Everybody agree with that? And 1 to any power is equal to 1. So this would just simplify down to a then, which is not an exponential function. That's a constant function, right? It's just y equals some value. We don't want to count those because we've already talked about constant functions elsewhere when we talked about linear functions. So we don't want to include those here. Does that feel okay? Now, why do we want to not include the negatives? Right, but we're saying we don't want to, b can't be negative. Why don't, like, what would happen if I did put a negative there? Like, why would that be a problem?
Wouldn't the exponent kind of mess with the negative value for b?
Sure, yeah. Sure, so one good reason is that, okay, so if b's negative, when x is an even number, you're going to get a positive number. But when x is a negative number, you're going to get a negative. Or as an odd number, you'll get a negative. Right? So the thing's going to just be jumping up and down across the x-axis. Well, that's kind of weird and not really what we want to describe, but that's not so much of a problem. But what would happen if, remember that x doesn't have to be a whole number, the variable? It could be something like a half, right? What does the exponent of a half really mean?
I think I'm wrong. Doesn't that like make the number smaller?
It might. The exponent of 1/2 is the same as a square root. And why would it be a problem if I had a negative number to the 1/2 power?
You can't do that.
I get an imaginary result, right? And can I graph something like that? No. Which is, again, why we don't want to have negatives in our value for b. Is everybody okay with that? So all exponential functions have a special key feature. They all have a horizontal asymptote. You guys remember what we mean by an asymptote? That's a line the graph approaches but never crosses. And since we're calling it horizontal, which way is that asymptote going? So left and right, horizontally, yeah. I just want to double check. Sometimes we get confused between horizontal and vertical. That happens. Everybody's cool with that, though? So for things of the form a times b to the x, the end behavior, or the, yeah, we have the limit as x approaches negative infinity of f of x is going to be 0. That's our horizontal asymptote. And the other end will depend on whether the a coefficient is positive or negative. So if a is positive, the end behavior would go to positive infinity. And if a is negative, it would go to negative infinity. Ooh, boy. I guess we should probably say a can't be 0 either up there. Right, because we just don't want to end up with 0. If a is 0, the whole thing zeroes out, and we're left with a constant function again. I guess we should say that there too. All right. Let's just do an example here. So let's say I want to evaluate the function f of x equals negative 2 times 4 to the x at a couple of different values. Okay. So first question I'm going to ask is this true? Negative 2 times 4 to the x. Can I just write that as negative a to the x? Definitely not. And the reason is because the exponents are different, right? The exponent on negative 2 is 1, and the exponent on positive 4 is x. You can't multiply the bases together if the exponents are different, basically because of the order of operations. 2 times 4, that's 8. But 2 squared times 4 is not 8 squared, right?
Well, you could do like 2 squared times 4 squared.
You could do that, though, yes.
What about, this is going to be dumb, but if it's 2 squared times 4 to the 1/2?
Nope.
Can't do that.
No. Not until you make either the base is the same or the exponent's the same, which you could in that case, in your example, because 4 to the 1/2 is just 2.
Yeah.
But in general, one of the two has to be the same.
Okay.
If the bases are the same, we multiply by adding exponents. If the exponents are the same, we multiply by adding the bases in. Okay. All right, so if I do f of 2, I have this. 4 squared is 16, and so I'd get negative 32. Everybody's cool with that? You could do that on your calculator a couple of different ways. So you could just do it, from the main screen. So -2 times 4 squared. Or if you're going to do a problem like this, where you're going to have to type stuff in over and over and over again, I might do it this way and type -2 to the 4x into my y equals, and then I can do vars over to y vars function, pick y1, and then I can do y1 at 2, and then if I hit second and enter, I can just go in and update that to all the different values that I have on my list. So it's kind of easy to do that. You know what I mean?
Wait, Mr. Cook, I'm confused. What are you substituting 0, -3, 1/2, -3/2?
Into the function y equals -2 times 4 to the x.
Is it going in for x?
Yeah.
X variable?
Yeah, so it's basically like the same function notation we're seeing here.
Yeah.
It's just the name of my function is like y1 of x.
Right, yeah, I don't know why I was tripping up.
That's okay. So you can do that, but I want to do it manually because I want to review some of these exponent rules that are going to be going on at the same time. So I think that that's going to be helpful for us. I just want to acknowledge that, yeah, there's a super easy way to do this on your calculator. All right, so I do f of 0, -2 times 4 to the 0. What's 4 to the 0? What? 1 is correct. Remember that anything other than 0 to the power 0 is 1. 0 to the 0 is undefined. So I do the same thing then for -3. So I plug that in. How do I do a negative exponent?
Don't you put the 4 in parentheses and do that thing?
It makes a reciprocal. And 4 to the 3rd is 64. And then how do I multiply 2 and 64? Or 2 and 1 over 64, excuse me. Jeepers creepers, Mr. Kulik. I wrote down what I mean. Getting it to come out my mouth, this was another question.
Can you put it in the calculator?
Well, to multiply fractions, you multiply the numerators and denominators. So it gives me -2 over 64, which reduces down to 1 over 32, or -1 over 32, excuse me. Okay. So the next one is -2 times 4 to the 1/2. What's 4 to the 1/2? It's the same thing as the square root of 4, which is just 2. Very good. Absolutely. Sure. All right. Last one. -2 times 4 to -3 over 2. Woof! How am I going to do this? Well, this is how I would think about this. I'm going to separate those out. Instead of thinking about that as 3 over 2, I'm going to think about it as 4 to the 1/2 and then to the -3rd. Because what's 4 to the 1/2? That's just 2. And then we can use our negative exponent property just like we did before, and then multiply our fractions and reduce. Is that okay. Now, clearly the calculator can handle all these problems. These are purely computational. You could type this into your calculator exactly as it's written and it'll just spit out the answer for you, no problem. The point of doing it by hand was to try to review some of these exponent properties because this stuff is important and it's easy to forget, you know? Yeah. Sure. Okay. Yeah, no problem. So, one thing that we'll be interested in doing is to be able to go from like a table of values to a exponential function. Oops. Okay, so let's say that we want to find the exponential function that has these points in it. So here's the easiest way to do this. This point is the key for me. So what I want is f of x equals a times b to the x. I want a value for a and b. Well, I know that 3, if I put that in for f of x, is equal to a times b to the 0. And b to the 0 is just 1. So I know that a is equal to 3. Cool with that? So then I can take any other of these points and do the same thing, plugging in for x and f of x. If I divide both sides by 3, I get that b is equal to 5. So I get that f of x is 3 times 5 to the x. Is everybody okay with that? Alternatively, your calculator can do this entire problem for you. What we'll do is an exponential regression using these points. So remember, we could do that by pressing the Stat button, choosing from the Edit tab, the Edit command. We'll fill in L1, or a list for our x coordinates. I'm going to use L1. So -1, 0, 1, and 2. And we'll have another list for the y coordinates. I'll use L2. And then we can, once we've entered in the data, if we exit out of there, go back to the Stat menu, but this time go to the Calc tab. And we scroll down till we find that exponential regression, EXP-reg, using the place where we stored our x and y data. For me, that was L1 and L2. I hit calculate. It tells me that A is 3 and B is 5. And it's a perfect fit because I can see the R values are 1. So you can do it that way as well. It's the same process, really. Well, no, it's not at all the same process. It's giving you the same result, though. The calculator does something much differently to come up with that. My suspicion is that the calculator linearizes the data and then translates it into an exponential using the same techniques that it does to build your linear regression and then translates it. But I don't know for sure. I'm not a calculator programmer, so. Another example is, let's say we give you just 2 points and neither one of them have the x-coordinate 0. Well, I'm going to, again, what I want to do is I want to write an equation. H of x is going to equal a times b to the x. And what I'm going to do is to create a system of 2 equations. Everybody's okay with that? What are some of the different ways we have to solve a system of equations? We just talked about this a couple chapters ago. There's 2 main algebraic methods, yes. Substitution and elimination were the 2 major methods we talked about. For this problem, I'm going to choose to use elimination, but the way elimination is going to have to work here is a little bit different than it worked when we studied it last. Last time, when we used substitution and elimination, we were dealing with linear equations, like 5x plus 6y plus 8z equals 10, where the exponents on the variables were all 1, and all the variables were being added together or subtracted. Here, notice the variables are being multiplied. So to do elimination, what I'm going to be doing is dividing the 2 equations. So I can either do equation A divided by equation B or equation B divided by equation A. Typically, what I like to do is I'm going to find the one with the bigger exponent and make that the numerator of my division problem. So I'm going to take equation B and divide it by equation A. It's fine to do it either direction. It's just a little bit more of a hassle if you go the other way and you use the smaller denominator or the smaller exponent in your numerator. So when I do that, I'm going to have 12 divided by 48 equals a times b to the negative 1 divided by a times b to the negative 3. Notice the numerator is equation B, and the denominator is equation A. Everybody's cool? I can reduce 12 over 48 to 1/4. And I notice that A divided by A is just 1. I don't have to write anything there. The A's have been eliminated. Everybody see that? And then how do I divide exponentials like this? If I have b to the negative 1 divided by b to the negative 3. Do you guys remember how we divide exponentials? Well, let's rephrase. If I have x squared times x to the third, what do I get?
6. No.
X squared times x to the third is, it's not, yeah, we add the exponents, we get x to the 5th. So if we add exponents when we multiply, what are we going to be doing when we're dividing? Subtract the exponents. So this will be b to the negative 1 minus b to the negative 3. Remember, the denominator is always going to be the one we're subtracting, which is why it's important that the smaller one, or makes it easier that the smaller one is the denominator. Everybody's okay there? I can then square root both sides. So I get that b is plus or minus 1/2. However, really, for exponential functions, We know b has to be greater than 0. So we can just drop the negative. Everybody's okay with that? That's halfway, right? That's the hard half. Now all we have to do is get a. To get a, I'm going to go ahead and plug my answer for b into either equation A or equation B. It doesn't matter. I'm going to usually just pick the one with the smaller exponent on b. Everybody's okay with that? So what is 1/2 to the negative 1? What do negative exponents do again? It's not a square root. They make reciprocals. So this is going to be the same thing as then 2 to the positive 1. Everybody's okay with that? The negative sign just makes the reciprocal and the exponent just becomes positive then. So a is 6. So if I put this together, I have 6 times 1/2 to the x. And here it's pretty important that I put a negative, or I put a parenthesis around the base of the exponential since it's a fraction. If I don't do that, if I write it like this, it's unclear whether I mean, is this x to the 1 over 2, or is it this, since those are two very different things. Is everybody okay with why this is unclear? Because you don't know. It's like, do you mean the x only goes with the 1, or is the x going to the whole fraction? Put a parenthesis there and just make sure that everybody's super clear. I want to point out too that again, this problem you could do just on your calculator, doing the same thing that we did for the previous one, just making a regression equation. So I'll take my x's and put in -3 and -1 into L1. And I'll put the y's into a list. I'll put those into L2. Exit out of there. And then stat calc exponential reg. My x list is the L1s and my y list is L2s. I do that and I get the same thing. The a is 6 and the b is 1/2. And notice the r values are exactly 1 or -1, so it's a perfect fit. Is that okay with everybody? Just pointing out to you that, like reconnecting this to things that we have done previously, right? We used those regression equations a bunch earlier. Just reconnecting it so that we can do that. Let's just kind of stop here for today. We'll finish up the rest of section 1 a little bit later after the test. But this feels like a good place to stop. As far as homework goes, I wouldn't worry too much about any of this, but realistically, you guys could do 1 through 8 at this point. I wouldn't worry about it too much. It's not part of any problem set that's due right now. It'll be for the start of next week's problem set. But realistically, you guys could do 1 through 8 if you're like, man, it's Friday night and I'm super bored. You know, like, I'm going to sit down and do my math homework. You know, if you're just like itching for something. There you go. Thanks, dude.
Of course, dude.
Okay. So I'm done with you guys.